All right, if you've ever really dived into physics, you've probably run into the beast that is the Irodov textbook, right? It's filled with these problems that are just famously tough, but also super rewarding. Well, today, we're going to take on one of the classics, problem at 1.209, a really cool puzzle about orbital mechanics. So let's jump right in. So here it is in all its glory, problem 1.209. Basically, it gives us a planet zipping around the sun, and it says, hey, at this one specific moment, we know exactly how far it is from the sun, how fast it's going, and the angle between those two things. And from just that one little snapshot, we're supposed to figure out the absolute closest and farthest that planet will ever get from the sun. It's a really great problem. Let's boil that down, right? The real question is, can a single snapshot of a planet's motion actually tell us the boundaries of its entire journey? I mean, that sounds kind of crazy, doesn't it? It's like trying to predict the entire plot of a movie just from looking at one single frame. But here's the cool part. With the right physics tools, it's not just possible, it's actually really elegant. Okay, so here's how we're going to break this down. First, we'll look at the planet's path and what the problem's really asking. Then we'll get into the two golden rules of physics that crack this thing open. After that, it's all about setting up the equations, solving the final puzzle, and then wrapping up with what we really learned from all this. Right, first things first. Before we write a single equation, we have to clearly lay out what we know and what we're looking for. Honestly, this is the most critical first step for any physics problem. So the problem hands us three key pieces of info at that one instant. We've got r0, you can call it r0 or r sub 0, that's our starting distance. We have v0, the initial velocity, and we have alpha, which is the angle between the distance and velocity vectors. Our whole mission here is to take those three things and find the two big numbers we're after, r max, the farthest the planet ever gets, and r min, the absolute closest it gets. Now, your first instinct might be to think, oh man, do I have to calculate the planet's position and velocity every single second to find the extremes? But here's the beauty of it. No, you absolutely don't. The secret lies in two incredibly powerful conservation laws. These are the cheat codes that let us skip all the messy step-by-step calculations. Seriously, these are the keys to the whole kingdom. Okay, so our first golden rule is the conservation of energy. Since gravity is what we call a conservative force, which is just a fancy way of saying no energy gets wasted on stuff like friction, the planet's total energy budget is fixed. It never changes. The second rule is the conservation of angular momentum. Gravity is a central force, meaning it always pulls straight toward the center of the sun. It never pushes sideways. Because of that, it can't change the planet's spin, so its angular momentum also stays constant. These two numbers, energy and angular momentum, are locked in. There are anchors. Let's zoom in on that energy part. The total mechanical energy, which we'll call E, is a mix of two things. You've got the kinetic energy, the energy of motion. That's the classic 1/2 mv squared. And then you have the potential energy, which comes from being stuck in the sun's gravity well. That's given by negative gamma mm over r. The sum of these two is the total energy, E. And the key thing to remember is that this number, this E, does not change, ever, for the whole object. And now for our second hero, angular momentum, m. For our purposes, its magnitude is pretty straightforward to calculate. It's the mass times the velocity times the distance times the sine of the angle between the velocity vector and the radius vector. And hey, for that initial moment, that angle is just the alpha the problem gave us. And just like energy, this value for m is also totally constant. But why is it constant? Well, think about it this way. The law says that to change something's angular momentum, you need to apply a torque, a twisting force. Imagine trying to spin a basketball. You have to push it on the side, right? You can't just pull it straight down. The sun's gravity is like that. It only pulls the planet straight in. There's no sideways twist, no torque at all. And if there's zero torque, the angular momentum simply cannot change. It's locked in. Okay, so we have our two golden rules. Energy is constant, angular momentum is constant. Now it's time to actually use them. We're going to translate these big physics ideas into some concrete math using the numbers the problem gave us. So let's start with energy. We need to calculate the value of the total energy, E, and we can do that using our initial snapshot. We just plug in our starting values. The energy E equals 1/2 m times our initial velocity, v0 squared, minus our initial potential energy, gamma mm over our initial distance, r0. Whatever number this calculation spits out, that's it. That's the energy of the system forever. We do the exact same thing for angular momentum. The magnitude, m, is just the mass times our initial distance r0, times our initial velocity v0, times the sine of that initial angle, alpha. And hey, quick pro tip here. A lot of students trip up on this. They forget the sine of alpha. You cannot forget it. It's so important because that initial velocity might be pointing at any old angle, not just a perfect 90 degrees. Okay, get ready because this next part is the aha moment. This is the key insight that just blows the whole problem open. Think about the orbit at its closest and farthest points. What's happening right at those turnaround spots? For an instant, the planet isn't getting any closer or farther away. It's moving perfectly sideways. That means its velocity is exactly perpendicular to the radius from the sun. The angle is 90 degrees. And what's the sine of 90 degrees? It's 1. And that little fact makes our math so much easier. So what does that mean for our equations at Rmax and Rmin? Well, the energy equation looks pretty much the same, just with a generic V and R that represent those extreme points. But check out the angular momentum equation. That pesky sine term just disappears because it's equal to 1. So at the min and max distances, m is just m times v times r. So much cleaner. All right, the heavy lifting with the physics is done. We've got our constant values for E and M from the start, and we have our simplified equations for the points we want to find. Now we're on the home stretch. It's just a matter of playing a little algebraic game to pull out the answer. So here's the strategy. At the extreme points, we have 2 equations and 2 unknowns, R and V. We need to get rid of one of them to solve for the other. The easiest one to eliminate is V. So we take our nice, simple momentum equation, mv equals mvr, and we just solve it for V. So V equals m over mr. Now we take that whole expression and substitute it right into the V in our energy equation. And just like that, poof, the velocity variable V is totally gone. We're left with one big, beautiful equation where the only unknown left is r, the very thing we've been hunting for this whole time. And if you squint at it a little bit, you'll see a term with r squared, a term with r, and a constant. Hey, that's just a quadratic equation. And what do we know about quadratic equations? They always give you 2 solutions, right? 2 roots. And isn't that just perfect because how many distances are we looking for? 2, a minimum and a maximum. So all we have to do is dust off the old quadratic formula, plug in our values for E and M, and solve. The 2 answers it spits out are exactly what we need. The bigger one is going to be Rmax, and the smaller one is Rmin. And check this out. This is the final answer, straight from the textbook. Now, I know it looks like a total monster, but don't be intimidated. It's literally just the quadratic formula applied to the equation we built. If you look closely, you can see it's made up entirely of the things we know, our constant energy E and our constant angular momentum M. It just proves that our strategy of letting the physics guide the math worked like a charm. So yeah, we solved the problem. Awesome. But what's even more important is the strategy we used. Because this isn't just a one-trick pony. This is a powerful framework you can use for tons of orbital mechanics problems. So let's just quickly recap the big ideas. Okay, here's the game plan for next time. Number 1, when you see an orbital mechanics problem, your brain should immediately scream conservation laws. Find the things that don't change, which are almost always total energy and angular momentum. Number 2, calculate the values for those constants using your initial conditions. And please don't forget that sine alpha term if the angle isn't 90 degrees. That's the most common trap. Number 3, identify the key insight for the point you're looking for, like how velocity is perpendicular at the min and max distances. And finally, just set your equations equal and let the algebra do the work. The physics guides you, the math gives you the answer. Look, this strategy we just went through, using conservation laws as your anchor, it's like a master key. It doesn't just unlock this one Irodov problem. You can use it to figure out escape velocities, to plot out satellite orbits, all sorts of cosmic puzzles. The physics gives you the fundamental rules of the universe, and the math is just the tool you use to see what those rules predict. So now that you have the tools, what are you going to solve next?